I'm Rishit, and I'll be talking about effective observability for MLOps pipelines at scale. Uh, and also, Shivai, who couldn't be here, he couldn't be at this conference, but he was supposed to be right there. So let's assume Shivai is here. Uh, okay, so yeah, let's talk about observability. And I'll start by saying that I'll be talking about both observability and monitoring. There's quite a bit of difference for it, especially for machine learning applications. And I'll start by talking about monitoring and then saying how much of it could reasonably be used for observability. So yeah, that's what I'll be doing. So all of this is pretty standard, and you might have used monitoring tools, observability tools for software. This is standard for all software, just to ensure that software is reliable and available. You meet the service level objectives. You make sure any system failures are properly diagnosed and all that. So usually the way you do this for traditional software is measure performance characteristics, and these could be a ton of different metrics. And what you want to do is just enable any quick reaction to system failures of any sort. So with that, I want to talk about why machine learning observability might be a different problem that you need to think about and solve. First off, there are sufficiently different challenges. So things like, for example, measuring CPU, for example, measuring CPU load and scaling up a node or scaling up your cluster might not work if you try to, let's say, run a PyTorch training job or a PyTorch inference service. If you have done it properly, it should use 100% of your GPU. So scaling up just based on that doesn't work at all. Because if you had done it properly, it would always be 100% or 0%. And there are also different challenges which are not related to the infrastructure. So you have model edge cases where there are probably particular cases where your model doesn't work well, and then you have things like data distribution and distribution shifts, misconfigured models, and the underlying idea behind all of this is the system works, you still get outputs, but so the model still makes a prediction and the user still sees something, but the predictions are not useful. So in traditional software, you don't account for this case at all. You just say, oh, there's like some 404 OOM seg fault, all of these. And yeah, that's probably bad because the user can't see anything, the system's not working. But over here, we have a different challenge. All of it is working, you get an output, but you need to somehow measure how good the output is. So that is the problem we have to solve. When trying to when trying to solve the observability challenge for machine learning. So let's take an intuitive look at what's happening. You have your machine learning model that learns some distribution from the data distribution, and you can have multiple things happen over here. So first off, you can have all of these different kind of distribution shifts. So you can have data shift where the training data you have represents something different than what you're trying to predict the model on. So maybe you could have an LLM trained on a very particular set of examples, and then you have a user who runs the LLM for something completely different, and you won't expect it to work very well. There is nothing like that in the training data. Then you also have that that your output distribution gets changed, but your inputs do not change. But your input distribution doesn't change for that output distribution. So this could also be a big problem, and you would end up producing pretty similar looking outputs for a lot of different inputs, and that's pretty bad as well. And then you could also have that your model changes, but the data distribution pretty much remains the same. So all of these are simple distribution shifts that can happen in these kind of models. And you want some way to measure these. And it's not straightforward how to do this because you don't. So I write quite a bit of stuff, but you don't have all of these values during uh, in the process of model doing some inference. If you had these values while you were doing inference, you would have like ground truth while doing inference, and you don't have ground truth. So some of these values are really hard to measure. And on top of this, you could also have feature changes where you probably have like some features in the model, some input features in the model that don't mean the same that they used to. So a simple example is, let's say you train a model to do something and one of its features is temperature, and you only train it in Austin where the temperature never goes below zero, and then you deploy it somewhere where the temperature does go below zero. So you have this feature change and label priors change as well in this example. I had like a ton of label priors that that the temperature there's no temperature below zero, and all of that changes when you change where your model is being deployed and how it is being used. And while this seems like a straightforward example, you will often see this quite a lot, even in large-scale systems which are trained on internet-scale data. They still have quite a few. They could still have quite a few distribution shifts, and I don't know if how much you have observed this with bigger models like diffusion models, stable diffusion as well, and LLMs as well. But it's pretty apparent that some of these do happen, and you can find out and you can find out problems that these big models have as well. Furthermore, you also have outliers and edge cases. So there's quite a bit of things that you need to handle to be able to properly do observability for these machine learning models. Usually for LLMs, the best way to handle this is, there's no good way to handle this. So you just say that your LLM can't generalize to out of distribution. So you train it on every damn thing. You train it on the test set. That's how that's how people currently train LLMs, because it can't generalize to anything outside of its distribution. But in any case, even though people do train models on these data, you still have all of these problems when you're trying to deploy machine learning systems. And it would be nice to find, and it would be nice to understand what kind of things you could do to observe this and then probably do some kind of decisioning around it. So another problem that you could have that could cause this category of problems to happen is messing up your feedback loops. And this is pretty popular. You especially have all of these models today that that probably give you some model output, and then you have the model output seep into the training data somehow. So that's like saying, oh, you have a diffusion model that generates some images, and the training data was generated by the same series of models. And that's often a big problem as well. This is particularly prevalent if you have tried to deploy any of these LLMs, especially some of these new LLMs. These are heavily filled with LLM data as their training data. And that not only that changes like a lot of training dynamics, which we do not talk about in this talk. We only talk about what happens at inference. So this already creates a lot of problems and changes up all training dynamics that you have. But this also messes up things in inference. You have these feedback loops cause really interesting outputs, like LLMs saying that they are some other LLMs, and all of this has been really popular as well. So this is also one of the causes of having this distribution shift. And while that's not like always a bad thing to do, uh, in most of the cases, these messed up feedback loops can cause quite a lot of problems. But there have been some really popular models like instruct picks to picks that solve a different problem and a different modality, and it's really hard to collect training data, and they essentially just and they essentially just use GPT-3 to create the training data set. And people have tried this quite a lot. So it's not always probably a bad thing to do, but it's important to understand that whenever you have these feedback loops directly affecting the same kind of problems, that's when that's when the outputs that's when the model distribution becomes really different than what you would expect it to be. So the reason why these kind of examples work, if you just think about instruct picks to picks, which solves the image to image problem. So you have an image, so you have an image, and you want to edit that image, and what it uses all of these LLM outputs for is just captioning the images. But what and the task that it's trying to do is and the task that it's trying to do is go from one image to another by progressively denoising it. So this is a different task, and that is why mostly these seem to work pretty well. However, if you are trying to solve similar kind of tasks, these kind of feedback loops can be quite a bit of problem. So we want to monitor all of these effects while our model is doing some inference, and this is often not straightforward because as I was saying, monitoring systems is simply checking for any of these. So can you use training metrics? It might be hard to directly use any training metrics that you have in machine learning models because you often never have the ground truth. And for a lot of cases, you have that the training metrics also don't make enough sense, especially for most modern generative models, especially if you see diffusion models. A lower training loss doesn't, or a lower loss in general, or a lower test loss even, doesn't amount to anything. You can have all of these LLMs perform better in terms of training metrics, and still the generations be worse because the training metrics are also not capturing the generation capabilities. So not only do most training metrics not work, not do what we want them to do, but these also are in a lot of cases just not possible. So if you are trying to measure stuff like accuracy of a model while inference, in a lot of cases it's just not possible because you don't have the ground truth. So what do you log then? Well, you of course want to start by logging the system metrics. But interpreting the system metrics would be really different. So this is an example where I was trying to train a simple NERF model, and I wrote the data pipelines myself. I wrote it properly. So even though I had a GPU with 80 GB VRAM, I pretty much had constant GPU memory usage the whole time, and around 100% GPU usage the entire time, just because I wrote the data pipelines properly. So interpreting these system metrics is also really different. And so you not only want to log the system metrics, but also make sure that you interpret them differently. And then you also want to log the model related metrics. So first you could most certainly log eval metrics. And then what you should probably do is also log the prediction distributions. So these were the three things we had been talking about earlier when we were talking about distribution shifts. And I didn't really show how you formally calculate it. I have some code on GitHub. That has how you do that. So go take a look at that. I I won't bore you with the specific details of it, but especially for model-related metrics, you would want to focus most of your attention towards eval metrics whenever you can get them, and finding out these prediction distributions. So, so you can interpret these prediction distributions like we were talking about them, and these would be good indicators of whether your model is performing well. What you can also do is monitor feature distributions and inputs. Often this is really hard to do. Often monitoring inputs is one of the hardest parts to do. But if you can monitor these and understand what kind of distributions of inputs you get in inference, that would be a direct. You can directly do observability from just monitoring your feature distributions and inputs. So, are these observability metrics or just monitoring metrics? I'm curious to know, what do you think of? Do you think these are good enough for talking about observability? Well, the answer is both. Yes. So the answer is yes, partly. You have all of these distribution shifts, which are excellent indicators of doing any kind of observability related tasks, and these also let you know, and these also give a lot of insight on decisions on when you need to retrain your models. So these distribution shifts are particularly observability metrics, and the other metrics we were talking about, eval metrics and feature distributions. Those are mainly just monitoring metrics. So let's see it in action. And that was just a quick overview of how do you tackle the large problem of observability in machine learning, and just a very intuitive understanding of how do you start working on it. So let's take a look at an example. So what I have over here is an example. Okay, let me just do .bash or see. I have some interesting aliases in there. Apart from this, what I have is I have 2 Kubernetes clusters here. Right now, I'm working in this Navigate NA 2024 live. So let me just switch to using that cluster. And now what I'll do is just go over showing how I try to monitor these. So first, what I'm doing is simply install Prometheus, Grafana, and Prometheus stack. And while this is happening, let's take a look at what we want to do. So super simple. We won't be talking about this. We'll create a simple REST service to expose the model. And particularly, we'll also, from the Kubernetes side of things, we'll instrument the server to collect metrics, which should be exposed via a separate metrics endpoint. We'll also use Prometheus instrumentators. They have good SDK support. And we'll deploy Prometheus to collect and store these metrics, and use Grafana to visualize the metrics. So all of this is from the Kubernetes side. And since I assume most people here would know about Kubernetes, I'll assume you all know how to do all this. What we want to do is plus all that we said we want to monitor. So I also want to monitor all that I said I want to monitor. And this is a pretty standard way of understanding what my server looks like. All of this is mainly just how Prometheus works, but I just have a separate metrics endpoint in the container I'm running, and that gives me all the things that I care about. Great. So let's take a look and do this. I particularly have a few. So most of the machine learning part of this is pretty much taken from a standard standalone example, and I don't have a lot of time to go into code. So what I'll actually do is I was planning to take a look at the code and probably show parts of it, but instead let me just switch to the instance I had running since a while and try logging into Grafana and see how our distributions look like and what we could probably infer from it. So let's just do .bashrc, and I had a demo instance. So this is an interesting internet test. If Grafana is able to load properly. So, okay, I've been trying to do. I've been doing port forwarding and just trying to run Grafana, but it seems the internet doesn't handle Grafana very well right now. So, anyways, what you would have this look like is something exactly like this, which is taken from what I see. So you'd also have you'd have different scores for this, and I've been doing load testing for this since the morning. So you'd probably have a lot of scores looking something like this, and you'd have all of your prediction distributions, training distributions logged in, and you could. Okay, I think it should be up now. Okay. So what it would look like is essentially just this, which is a screenshot from what it looks like. And there would essentially just be a lot more data, and you'd have all of your prediction distributions, training distributions, feature distributions logged in, and you could understand insights about how your model is performing from these distributions instead of any eval metrics and so on. So that's how it looks like, and give it a try yourself. So that's about the talk, and if I have time, I can probably take like a few questions, or you can talk to me later.